So in 5.1, we'll find areas using Riemann sum. We'll not be doing any integrations as yet. We'll just be finding areas using Riemann sum. Okay. So what's that? Let's say you have a graph like this. You have a curve. Let's say v equals t squared. Okay. And I want to find or approximate the area under this curve. Okay. I want to find the area under this curve. So if you remember, integration gives us the uh, method, or gives us the freedom, I would say, to find the area. If we can integrate smaller areas, we actually get uh, the area of the bigger picture. But what else can we do? Obviously, integration is more accurate, but geometrically, we can do this type of approximation. We can draw rectangles under that curve, and then we can find the areas, I should say, because it would be more than one rectangle in most cases. So if we can find the area of those and add those together, then we can approximate the area of the area of the uh, entire space under the curve, right? This is the uh, most naive approach of finding area under a curve. We'll slowly build up towards how to find using the integration method. Okay, so now what's the method? What's the methodology here? What should we do here? So for that, I want you to have this slide open in front of you, and I'll show you the calculation. Okay, let me do that for you. Just give me a second. Let me start sharing the screen of my iPad. There you go. Okay, today is, I believe, 29th. Okay, so if you have a curve like this, we can draw, let's say, like this. We can draw rectangles like this to find the area, right? Or we can do this. You see the differences here? Can you locate any difference when I'm trying to draw rectangles? When I'm trying to subdivide the area under the curve into some uh, rectangles, can you see the differences in the rectangles? I'm not doing any calculation as yet. I'm just trying to show how to draw these rectangles. Can you look at any differences here? Anyone? if I zoom in, sorry, you'll be able to see it better. So in the first case, I went like this, right? Like this. That means if I find the area of these rectangles and add, don't you think I'll have some additional area as well over the curve? Do you agree? I'll have some additional area, right? Remember, I'm trying to find the area under this curve, okay? So if I add the areas of these rectangles, I'll have additional areas because of this yellow portion. Do you agree? Because it's actually over the curve. Do you agree? I'm not sure if someone is trying to say anything because I haven't heard a single word as yet. I was wondering if the uh, sound system is working fine. Can anyone try to say something?
We can hear you.
Yeah, that makes sense.
Okay, so that means we say that we are overestimating. This is an overestimate. Do you agree? Because you can see this additional part, yellowish part, is actually over the curve. It's not under the curve, which we're trying to find. So if we add the areas of these rectangles, we'll have that yellowish part, which is not in our territory. We don't really want that. Since we are approximating the area under the curve, that means those yellowish part will give us an overestimation. Do you agree with that? Or does it actually make sense? And if I do this way, uh, if I do this way and find the area under the curve, let me show you what happens. This is the areas of the rectangles which will be adding to approximate the area under the curve. But if we do that, once again, we'll have this. I think I should change the color. Uh, we'll have this sky blue part here, which will not be included in our approximation. Do you agree? These three sky blue, as you can see, it's actually under the curve, but it's not really included in the rectangles we have drawn. We'll be just adding the areas of the rectangles. So those sky blue portion will not be added to our approximation, right? If we draw rectangles like this, and we say this is an underestimate, that means we are underestimating the area of uh, the area under the curve, I would say. First of all, does it make sense? Then we'll move forward. Any question from this? Because you'll definitely see questions like this in the homework and in the exam as well. Okay, a graph will be given and you'll be asked whether it's an underestimation or overestimation. So my question now is, can you eyeball the graph and say whether it's an underestimation or overestimation? If yes, then obviously it's fine. If no, then I'd like to reconvince you. Okay, you'll definitely see a question like this in the exam, no doubts. All good? Okay. So if I give you a graph like this, let's say, okay, let me draw a very good one. Okay, like this. Okay, let's say you have a graph like this, and I'll obviously provide the rectangles as well. Let's say you have rectangles like this. And oops, okay, now can you um, locate whether it's whether it's an underestimate or overestimate? Can you locate for me? Let's say let me give you the points as well. Let's say this is pi over 6. This is pi over 3. This is pi over 2. Okay. Can you locate the underestimation part and overestimation part? Who wants to try?
It's overestimated at pi over 2 and underestimated at pi over 6.
Okay. So you're saying, so I think you have found a really good issue here. Is it can't be overestimate or underestimate either way at a single point. It actually works on a certain interval, right? It doesn't really, it's not really working at a single point, because remember, you are trying to find area. So it can't be a single point. There has to be at least 2 points for it. So I understand what you're trying to say. So we can clearly see that on this portion, we'll have an overestimate, right? So from pi over 3 to pi over 2, we'll have an overestimate. On this portion, we'll have an underestimate from pi over 6 to pi over 3, right? And again, we'll have overestimate here. So I'm using this yellowish color for overestimation and this red color for underestimation. Do you agree with this? Do you agree? Does it actually make sense? Or if I ask you directly, if you see a question like this in the homework or in the next exam, will you be able to sort it out? Will you be able to solve this with full confidence? Any question from this?
My only question is from from 0.0 to pi over 3.
Mhm.
Even though we have an overestimate and an underestimate, it would like come out as an underestimate, I think. Or do we need to write like overestimate from 0 to pi over 6 and then from pi over 6 to pi over 3 under? Like, can we combine them or no?
No, you can't really combine those, because you never know what will happen. Since we're just trying to sort out where it's an overestimation and where it's an underestimation, we're not really calculating how much overestimation we're having here, or by how much we are underestimating it. So since we are not really calculating it, you can't really combine. Yeah, that's a good question. Because you can clearly see, if we combine these two, I'd say, from 0 to pi over 3, for example, this portion, the underestimation part at least looks bigger than the overestimation part. So you're right, yeah. If we had combined this, the overall would have been an underestimation. That's true, but we're not really calculating it. That's a good question anyway. Anyone else? Okay, now we'll see at least 3 formulas to solve, or to use to find or to approximate the area under the curve. Okay, and these 3 formula will be needed for the next homework. Okay, all you'll be doing to use this formula and finding the area under the curve. This is these 3 formulas we'll be using the next time. But before that, since I said 3, I'd show one more thing. Oops, someone in the waiting room. Give me a second. Okay, so I've already showed you these 2 scenarios, right? Scenario 1, scenario 2. But I can show you one more. Let's see, you have this. And instead of going like the way we have gone on these 2 cases, let me try this way. So let me use the middle part of the rectangle. Okay, now we'll be using the middle part of the rectangle. That means it will look like this. So the middle part of the rectangle means half of the length will be, I mean this length, by the way, this length. Half of this length will be under the curve and half of the length will be over the curve. Okay, this could be another scenario. Don't you agree? So we will be developing a formula for each of these. and we have certain names for this, fortunately. Okay, so how can we define it? That's the first question we want to ask. So if we have a scenario like this, we call this a left Riemann sum, or in short, a left sum, because we'll be starting from this point. We'll be starting from the very left point of the interval. Now, how can we find the interval? I'll go there, but let me try to find the names first, okay? I'll go there, how to find how many intervals will be there, how big the intervals will be, right? We want to know that as well. Okay, so if we start like this, that means for the underestimation, we call it the left sum. But here is the thing. What if my graph looks like this? If we can start from the left point, then you will see it will be an overestimation. So it actually depends on how the graph looks like. So instead of saying underestimating, I think I should say, if we start from the left point of the interval, okay, then it will be the left sum. So you'll have certain intervals to work with. Let's say A and B. We'll subdivide it into several parts. But if you start from the very left point, we'll say that this is the left Riemann sum. Okay, and if we start from the right point, if we use the right points, then we'll say that this is the right Riemann sum. Okay, so clearly you can imagine the name of this scenario would be midpoint Riemann sum, right? Because we'll be using the midpoint of the interval. This is how we define these scenarios. Okay, now slowly we'll go to how many intervals we'll be doing and what will be the length of that. That would be another case. That would be another case. Obviously, the number of intervals will be provided, or the length of the intervals will be provided. Either of these will be given. You'll need to figure out the other. Let's see how. Okay. So if you have an interval, like let's say from A to B, okay? If you have an interval like this, the question will say subdivide this interval into three intervals, or rather divide this interval into three sub-intervals. Okay, whatever you have, the question will say find the Riemann sum by dividing this interval into three sub-intervals. Okay, now we know that we need to divide the interval into three parts, but the next question would be what will be the length of the sub-intervals, and the reason you need the length is this. We are trying to approximate the area of, or rather I would say under this curve, using the area of the rectangle, right? Remember, we are using a rectangular shape. And what's the area of a rectangle? Anyone?
Length times width.
Length times width. Very good. So it's actually this one. If I say, I'm running short of color from here, let me use a color from, okay. If I say, I'm just looking for this length and this length, do you agree? Because this is my length times width. Do you agree? Right? And if this is my interval, let's say this is negative pi over 2. If this is my interval from negative pi over 2 to pi over 2, I should use this because the values will be included. Anyway, so I'll be subdividing this interval into equal parts, okay? Although my drawing doesn't give you an idea that these are actually equal to each other, these lengths. But this will be equal to each other, okay? If you draw it properly. We'll be subdividing the interval into equal parts. So these lengths will be the same, okay? We want this length to be equal to each other. These lengths have to be equal to each other, okay? And we know the area of a rectangle, we'll draw it again. The area of a rectangle is length times width. This is the length. And where does it come from? It comes from this, the length of the subinterval. Can you see that? Or do you agree, I would say? For finding the area of those rectangles, you need the length of those rectangles. Or in other words, you need to know the length of those subintervals. That's why I keep saying that we need the length of the subintervals. Does it make sense? Remember, we are slowly building towards the formula. Does it actually make sense to you that how to use this length, or what are the reasoning behind this? Okay, if you agree that this should be the length for the rectangles we have, then let me show you how to find the length. So the length of the interval will be the difference over the number of intervals. So this will be the length of each of those subintervals. Okay? So you need to find the length of the main interval. That means if your interval is from A to B, if you subtract A from B, you'll get the length of the entire interval, right? Then if you divide it into how many parts, how many subintervals you need, then you definitely get the length of each subinterval, right? Simple algebra though. But anyway, we are trying to build up towards our main goal. Any question from this? Does it actually make sense? Don't try to convince yourself if you're not completely convinced, okay? Because this is tricky. This is easy, definitely. I'm telling you, when you'll be doing it for the 5th time, 6th time, or after doing 2 or 3 practice problems, when you'll be doing it, you'll find it really easy. But it has some issues which you might encounter if you don't understand it completely, okay? All right, now we know how to find the length of each of these intervals. What else do we need? What else do we need to find the area of these areas, I should say? But let's take one at a time. Let's say we are trying to find the area of one of these rectangles. Then we'll add the others, right? So we know the length of the rectangle. How to find the height or width, whatever you say. I think height would be a good choice here. How to find that? Or which length we are talking about? Which length we should consider if we're trying to find the area of this rectangles? This is one of the lengths. Obviously, by length I mean the sides of the rectangles. Okay, so let's say this is one of the lengths I have. I need one more, right, for finding the area of the rectangle. Which one should I pick? I wonder why there is that awkward silence today. No one is really contributing. Are you feeling sleepy? Is it the exhaustion of the last exam? Let me ask from the participants list. Okay. Okay, Brody, can you hear me?
Yeah, I can hear you.
Okay, so is the question clear? I mean, what I'm asking?
I showed up a little late, so I'm trying to catch up and figure out what we're even doing.
So we're trying to find, let's say, the area of this rectangle, okay? And we have this length. What else we need to find the area of this rectangle?
The other leg, so say that's the width, we need the length, which would be the peak of the arc.
You mean this one, the green?
Yes.
Exactly, right. So we actually have two sides, right? For a rectangle, these opposite sides are equal to each other. So we already have this length. Now we need the other length, right? And if you can multiply these two lengths, obviously, let's say this is my width and this is my height. If we can multiply these two lengths, I'll get the area of the rectangle. So we already have this length, no worries with that. How do you think we can find this one? If you can figure this out, our formula will be here. This is the last thing, not the last thing, but the penultimate thing we need. How can we find that length? Anyone? Just give it a try.
Would it just be f of x at that point?
Very good, exactly. Yeah. This is f of x. because that's the functional value at that point, right? Because, oh, this graph looks really clumsy. Let me try. Because this length, as I said, this is equal to this, so this is equal to this, and this length, you can see it is touching the curve at its peak. So that means it's like this. This is the length we are, just for example, this is the length we are trying to find. And since this is just the touching point, or rather I should say the intersecting point of the curve with this line, I should say touching because it's not really going intersecting it anyway. So this is actually the functional value at that point. Let's say that's A. So this is definitely f of A. This is the functional value at that particular point. Do you agree? If I say this is the functional value at that point, do you agree with that? Okay, now we are almost there. We're almost there. So we know how to find the length. We know how to find the height, or the other length, I would say. So that means we can just find the area of one of those intervals, sub-intervals, I would say, by this. Del x times the functional value. Do you agree with that? This is the area, right? This is one of those lengths. And this is the other length. If we multiply these two lengths, we get the area of the rectangle. And then if we can add those rectangles, the areas of the rectangles, we'll get our Riemann sum. We'll have three different formulas as I promised, but this is the way we'll be this is the way we'll be finding the formula. Okay, because the idea is the same. This is the general idea. That means we need two lengths, the width times the height, and this is the way to find that, the length of the subinterval and the functional value. This will give us the area of a certain rectangle, and if we can add, doesn't matter how many rectangles we have, if we can add the areas of those rectangles, we'll get our result. Do you agree? Don't just trust me, okay? Try to understand why it's true, why I'm saying this. Because it definitely doesn't look like the area of a rectangle anyway, but it is, right? Okay, now the last thing we need to have the formula for the three types of scenarios we have seen. What's that? And for that, I need to draw the graph again, I'm afraid. Okay. Sorry about that. Okay. Now, let's say we are subdividing this interval from 0 to, let's say, 3, okay? We're subdividing it into 3 parts, okay? So the first job is to find the length of those intervals since we are dividing into 3 parts, the length of each of those intervals will be 1. Okay. Now, the question would be whether we're trying to find the left sum, right sum, or the midpoint sum. So let's start with the left sum. As I said, we'll start from the first or the leftmost point, right? So our interval is from 0 to 3. We'll have 3 intervals. So you can clearly imagine it will be like this. Do you agree? Right? Excuse me. Okay. Now we'll be starting our calculation. So it would be, I think instead of giving it a 0, let me give it a better look. Instead, I would say this looks like this. Oh, not again. Yeah. So we'll start from this point, and then let's say this is my 1, this is my 2. So we'll go to 1 and draw a rectangle. Then we'll go to 2 and draw a rectangle. Then we'll go to 3 and draw our final rectangle. Right? Okay. And the length, of course, will be this, we know. And we have already found out it's actually 1. All we need now is the height. And now this will come handy. Since we are finding this way, since we are finding the left sum, as I said, you'll see we'll be taking this left side of these rectangles. And you can clearly imagine why, because you can see the right side is not actually the functional value because it's not really touching the curve. Rather, the left side, you can see it's touching the curve. That means at that point, we'll get the functional value. Does it make sense? We want the functional value, right? This height will not give us anything, right? Although these two are equal, but we can't really calculate the right side because it's not really touching the curve. How am I supposed to find the functional value then? So we'll be using the left side of the rectangle to calculate it, right? So this is the functional value at 0. This is the functional value at 1. And this is the functional value at 2. Do you agree? Don't really trust me. Do you agree with that? Who doesn't agree? Who wants me to clarify this again? If you agree, then if I say the left Riemann sum is going to be del x times f of 0 plus f of 1 plus f of 2, will you agree with me? Because this is the length times height, length times height, length times height. Since the del x is the same, I'm keeping it, outside like this, factoring this out. You can even write like this. Okay, del x times f of 0, del x times f of 1. If you want, but since this is the same, you can factor this out and write it like this. It's even convenient, even more convenient, right? So this is the left Riemann sum. That means when you are calculating the left Riemann sum, you'll start from the leftmost point on the interval. Okay, and keep doing this. And go to the xn minus 1. Oops, I think I should write del x here, not only del x. Yeah. Why is that xn minus 1? This is, sorry about that. This is actually x0 to xn. This is your interval. You might be wondering why this is x minus 1. So you can clearly see the last functional value we need is f of 2, which is this. We don't really need the right end point of our main interval. Can you see that? We start from the left end point, but we don't really go to the right end point. We actually end before that. That's why it's n minus 1. If we have up to n, we need the functional value just before that, up to the previous one precisely. You don't need to memorize it though. If you can understand how it's working, that means why do you need this length, or rather how to find the length, then you're done, because this length will give you the functional value, right? Again, this is equal to this, no doubts on that. But if you consider this, you'll not be able to calculate the functional value because the curve is not really touching that. So if you want to calculate, you need to calculate this, the left point of each interval. That's why it's left Riemann sum. Clearly you can see we are taking the left end points of each interval, as you can see, 0, 1, and 2. This is actually the left end points of each of those subintervals. That's why it's the left Riemann sum, okay? Doesn't matter what the curve is. Okay? All right. So if I say the right Riemann sum, can you imagine what could be done here? So instead of using the left endpoints, now we'll be taking the right endpoints. So this will be the functional value starting from, not starting from x0, you can see. We'll start from the next one, x1, and we'll keep going up to xn. That means we'll be taking these three values for the right Riemann sum. Okay. So for this particular problem, let me use the space above. Okay. All right. All right. If we use the space here, the left Riemann sum, the right Riemann sum, I should say, is going to be del x times f of 1. Since the right endpoint is 1, 2, and 3, you can clearly imagine it will be f of 1, f of 2, f of 3. These 3 points, right? Does it make sense? Okay. And the graph will look like this. Let me show the graph as well of the same curve, of course. So now, this is 0, right? 0, 1, 2, 3. So we'll be starting our point from 1. We'll go like this. Then we'll go to 2 and go like this, then it'll go to 3, go like this. It doesn't look right because of the, okay, it will look like this, although these rectangles will be equal to each other. Since I'm drawing it by hand, I have kind of messed it up, but you can clearly imagine it will be the same length. Oops, sorry. These lengths will be same. It's 1, 2, and 3, right? And again, to find the functional value, we now need this length. You can see this is actually touching the curve, right? That's why we'll be taking the functional value at 1, 2, and 3. That's what we have done here for the right Riemann sum. And for the midpoint, you can clearly imagine we'll be taking the how would I define this? I think I should use another notation for this. Let's use C1, where C1 is the midpoint of the first subinterval, okay? That is x0 plus x1. And we keep doing like this. This is the midpoint of each of those intervals, nothing else. Okay? You'll be given a function, you'll be given the interval, and you'll be told either that means you'll be given this b and a, that means the interval, and you'll be given either n, that means the number of subintervals you need, or the length of the subintervals. In most cases, I guess n will be given. You'll be given a function. That's the first thing. Second thing will be the interval. Third thing will be either of this. You'll be given 3 informations, and from this, you'll be asked to find the Riemann sum, either the left one, the right one, or it could be both, or even the midpoint. I could ask you to find all 3 of this for the same function in the same interval for the same number of subinterval. I'll say, hey, can you find the left Riemann sum, the right Riemann sum, and the midpoint sum for me? And then tell me which one you think is better, which one gives you the better estimation. Okay, any question up to this? We'll be solving a problem soon after the break. We'll be going for the break, but any question up to this? How to find or I would say how to approximate or estimate the area using Riemann sum. Any question? Any question on how I formulated this? Does it make sense? Everyone?
It makes sense.
Okay, again, take your time. Let's meet 5 minutes. Let's take a 5 minutes break, and then we'll be solving a couple of problems, at least one, hopefully, and hopefully it will make more sense, okay? All right, see you at 10:15. Isn't it the midpoint of each of those subintervals? The midpoint of each of these subintervals, right? If you remember, I did mention that. So if this is your interval 0 to 2, what's the midpoint of 0 to 2?
1.
1, exactly, right? How to find the midpoint? Of course, add those two and divide. Same goes for the other one. Add those two and divide by 2. just find the midpoint of each of your intervals. That's it. So that means on this occasion, we'd need f of 1 plus del x times f of 3. Do you agree? We just need to find the midpoints and take the functional value at those. Okay, what's the midpoint, or what's the functional value at 1? It's 1 squared, right? And what's the functional value at 3? It's 3 squared, so it's 9. So 2 plus 18 is 20. So this is the left Riemann sum, this is the right Riemann sum, and this is the midpoint Riemann sum. Take your time and see if you have any question from this, okay? Any question? No questions at all? Is it super easy? Okay. Let's create the breakout room and give you a problem to work. Okay, so let me see how many lectures we have. We have 5.234. No, I think we should go for the next slide now, but I'll give you a problem to practice, okay? And I'll provide the solution as well so that you can cross-check your work. All right. So before you start the homework, you can practice this to see yourself. You can practice some other problems from the book as well. And you should definitely practice 1 or 2 before you start the homework, okay? Which I'll be posting hopefully tonight. I have to post it tonight anyway. Yeah, I'll definitely post it tonight. Okay, your interval is -π/2 to π/2. Your function is cosine x, and you need to find all these 3: left Riemann sum, right Riemann sum, and midpoint Riemann sum. Okay, for 3 subintervals, that means n equals 3 for 3 subintervals. And let me give you the solution as well. The midpoint sum would be, I guess it would be 2π/3. Okay, let me show you the decimal value. It's 2.09. It's close to 2.09. The left and the right both would be 1.81. Okay, just cross-check your work for this function cosine x within this interval -π/2 to π/2, and you need to divide it into 3 subintervals. Okay, all right, give it a try and let me know. Okay, let's go to our next slide, which is 5.2, and which will be really, really easy. Just will be adding the definite part of the integrals. We have seen the indefinite integral before, but this time we'll be finding we have seen the indefinite integral, I would say, but this time we'll be finding the definite integrals. That means we'll have certain values, certain area, certain interval, I would say, where we will be looking to find the integration, looking to integrate the function. Okay, so now why did I say that the integration gives us the area? Let me show you the graph of that, the graphical representation. In the Riemann sum, we have drawn rectangles like this and found or rather approximated the area, right? And it was not really that good because you could see we encounter overestimation and underestimations. But if we can integrate it, let's say it's my A, it's my B, if we can integrate it, it will actually give us the exact area of this. Okay, the exact area under this curve. So that's why we use integration instead of Riemann sum to approximate or to find the area. Integration gives us a better approximation, better estimation. Okay, and to do that, what we do is excuse me, is we consider this as really smallish rectangles. That means instead of dividing this into 3 intervals, what if I had divided it into 50 subintervals? So we'll be extending the idea of Riemann sum for the integration. Let me show you how. So for Riemann sum, we did it like this, right? We divided the interval into, let's say, 4 rectangles like this. But what if I would be able to do like this? I divide it into 50 really small rectangles, small in terms of the length. Then don't you think we'd be able to remove the possibility of overestimating and underestimating? That means if we can keep this length really small, this extra area, this area where we would have underestimated or overestimated, this place could be removed. We could get rid of this place. The more subintervals you have, the better approximation you have. Can you see that? So if the length is pretty small, it's really small, that we say it goes really close to 0. The length of the subintervals tends to 0. Then don't you think the estimation would be even better? And that is actually when the subinterval, the length of the subinterval is pretty close to 0, the Riemann sum is actually this integration. I should write it this way though. Let me change the order. It doesn't really matter though, because it's a product, but I should keep the consistency. Yeah, if it's really small, it's really really small. That means it tends to 0. Then we say this is the integration of that function. Or I write this way. I can say this is from, sorry, I equals 1 to n. And if n tends to infinity, that means you're subdividing it into infinite number of subintervals. That means so many rectangles here. Or in other words, del x is really small, which is close to 0. Whichever way you think, it actually tells you the same, gives you the same idea. When that's the case, this is actually how we define this integration on that interval. Okay, let's say a and b, our interval is a and b. So we say this is the integration from a to b of that function. So we have developed the Riemann sum to reach this new conclusion, which we say integration or finding antiderivatives. We'd be finding definite integrals. Why? Because you can see we'll be getting the result within a certain interval. Unlike the way we did the last time in 4.9, we didn't have any certain interval. We just found the general antiderivative. But instead, we'll be finding it in a certain interval, in a certain region. And it will give us the area on that interval, okay, within that interval, I would say. Okay, let me show you one example of it, and hopefully you'll find it really easy because it's the same idea. We'll be finding the antiderivative the same way we have done in 4.9, but we have some additional work to do. You can see, since we have a certain interval to consider. Okay, so let's say we are trying to find, let us use the same function, okay, and let us find the same interval as well, from 0 to 4, okay. So from 0 to 4, we'll be trying to integrate or trying to find the definite integral of this function. So what should we do? So that means we start with the left-hand point. This is the lower limit. We call this as the lower limit. And we'll be writing the right-hand point here. We call this is the upper limit. That means we have a limit. We have limitations. So we shouldn't go beyond these 2 points. We have to limit ourselves. We have to hold ourselves back and don't go beyond this. Okay. And if you remember, it's the function times, I shouldn't say times, this is the notation of integration. If you remember, we did say that in 4.9, we have to write the function here, which is x squared. So we're trying to find this. Okay, let's do that. What's the general antiderivative of x squared? You should know that. You have done this. The antiderivative of x squared. Anyone?
Is it 2x plus c?
No. So 2x would have been the derivative, not antiderivative.
Oh.
No worries. Anyone else? The antiderivative of any function of this format, x to the n, using the power rule.
Isn't it 1/3 x cubed.
Exactly, yeah. So the formula is x to the n plus 1 over n plus 1. So x to the 2 plus 1 over 2 plus 1. And again, if you remember, if we had an indefinite integral, then we would have written a plus c, right? But it's not. It's a definite integral. We know that because we have a certain interval to consider. So we'll not be writing this c anymore. Instead, that's the additional part I was talking about. The antiderivative part would be exactly the same as we have done for the indefinite integrals. But for the definite integral, instead of writing c, we'll be evaluating this within this interval. We'll be using this sign. This means whatever you have here as the antiderivative, you need to evaluate that antiderivative at these points. Okay, so that means if I do that again, you just write a vertical line like this and write the limits in its respective place. Okay, that means you are evaluating this antiderivative at these points. Now, how to do that? Before that, let me simplify it just a little bit. It will be x cubed over 1 over 3, right? X cubed over 3. Yeah. Okay, so we can keep this 1/3 outside. Now, since we are evaluating something at a point, that means we'll be plugging it back into the place of the variable, right? That's general evaluation. That's how we evaluate something at a point. We'll be plugging in the value in place of the variable we have. So it will be x cubed, that means 4 cubed and 0 cubed. But since we have two limits, what we do is evaluate it in the upper limit at the upper limit and subtract the evaluated value at the lower limit. That's it. That means you evaluate it at the upper limit minus you evaluate it at the lower limit. That's it. That means it gives us 1 over 3, 4 cubed is 64, I believe. And obviously 0 is 0. So 64 over 3, it should give us a fraction because it's not divisible by 3 anyway. So I assume it would be 21.3. So the area of x squared within this interval 0 to 4 is 21.3. Now let's see what did we have when we tried Riemann sum. You can see we had 8 when we used the left Riemann sum. We had 40 when we had the right Riemann sum, but we had 20 when we tried the midpoint Riemann sum. And it's the closest. Can you see that? Because our main answer is 21 point something, 21.3, and the midpoint approximation, or I should say midpoint Riemann sum, gave us 20. So in most cases, you will see the midpoint gives you the better estimation. Okay, the midpoint is better. In most cases, you will see that. Any question from this problem? I mean, how did I find the antiderivative? How did I evaluate it at the upper limit and the lower limit? Any question from this? Take your time, okay? Just find the antiderivative the way you have done for 4.9, I mean for indefinite integrals, then evaluate it at the upper limit, evaluate it at the lower limit, just subtract the latter from the first one. Okay. No questions at all? Let me show you one more example and hopefully it will make more sense, right? Yeah, let's try this one. F of x equals to, let's say, 3x squared plus 2x plus 1. And we want to find the area from 1 to 3 within this interval 1 to 3. Okay, so that means from 1 to 3, we'll be trying to find 3x squared, 2x plus 1, the integration of this, right? Okay, now let me help you with this. Since we have more than one terms here, we have actually 3 terms precisely. What can you do? Anyone? Just give it a try. It's
Make it
pretty
by the sum rule.
exactly very good. We have done this for derivatives, we have done this for indefinite integrals. It's the same. So we can use the sum rule. Since we have more than one terms, we can subdivide it into several, number of terms we have. So 3x squared dx, although you don't need to show this step, I'm showing this because most of you will be doing it for the first time. Oops, sorry, I should write dx here. And from 1 to 3, 1 dx. That's it. Now, let's do it one by one. Okay, what's the derivative of 3x squared? Or I would say, I think I should ask this way, how to find the antiderivative of 3x squared? Anyone? What if I can write this way? Although you don't need to, but for your convenience, I'm writing it this way. I can keep the constant outside, right? We have seen this. Now what's the derivative of x squared? We know the derivative of x squared is 2x, x cubed over 3, right? So 3 times x cubed over 3, we need to evaluate it between 1 and 3, plus what's the antiderivative of x? Can use the same rule, power rule, of course, power rule of finding these integrals. Anyone?
X squared over 2.
X squared over 2. You need to evaluate it between 1 and 3. What about this? The next one. What about this one? What's the antiderivative of this? We have nothing here. What does it mean? Doesn't it mean x to the 0? Because x to the 0 is 1. You can rewrite any 1 by x to the 0 or anything to the power 0. We can replace it, right? Using the power rule, it gives us 1. Because x to the 0 plus 1 over 0 plus 1 is x. Any question before we go to the evaluation part? Any question? No question at all? Okay, before we evaluate, we can simplify it just a little bit. We can cancel this 3 and 3. We can cancel this 2 and 2. So we just need to evaluate x cubed, right? So if you remember, we need to evaluate it at the upper limit. So replace x by 3 minus, we need to evaluate it at the lower limit. So replace x by 1. Right? Excuse me. Same goes for the next one. Replace x by 3 minus replace x by 1. And last but not the least, replace x by 3 minus replace x by 1. Just in place of x, write the upper limit first and then subtract the lower limit. Okay, if you have exponents, you need to have the exponents as well. Just replace your x, nothing else. If you have cubed, have those cubed. If you have x, if you have squared, have that squared. Okay, like this. Okay, let us see what's the evaluation gives us. So 3 cubed is 27, 1 cubed is 1, 3 squared is 9, 1 squared is 1, plus 3 minus 2 is 3 minus 1 is 2. So it's 26 plus 8 plus 2, so it's 36. So the area under that curve from 1 to 3 is 36. Any question from this? Take a look at this, okay? Take your time. You don't need to be in a hurry all the time. Just breathe in, close your eyes and see this problem again and see if it actually makes sense. Everyone, does it make sense? Any question from this? Real quick. No questions at all? We are almost to the end of the semester. I know you are feeling really tired, and it's a super boring lecture, I know. Some of you might be feeling sleepy as well as you, if you have studied late night. So again, but if you contribute it, if you interact with me more, then this boringness, this boredom, I should say, this boredom might be reduced to some extent. This might feel lively for a fraction of a second, maybe. Anyway, let me show you 2 more really funny, or I would say interesting properties, and then we'll wrap it up. So the first one is from a to a, your integration, whatever the function is going to be 0. I'll show you why. So if we have a curve like this, let's say this, okay, and from a to b, you have an interval. If you're trying to find the area under this curve from a to a, what does that mean? You start from here you are ending at here, ending at the same point. Can you get an area for this? All you get is a length, right? You actually get a length, nothing else. You can't get an area for that because you start at this point, you end at this point. You're not going anywhere. You are actually standing at the very same place. How can you get an area for that? Right? So it actually gives you 0. Or if you think about the geometrical aspect, you need this length, right? On this way. You have this height, no worries, but you need the width as well, the length in this direction or in this direction, whatever it is. And I can't see any length here, so this length is 0. So whatever your other length is, if you multiply it by a 0, won't it become 0 as well? Doesn't matter how big this is. Do you agree? So that's a pretty good property you can use in some of the problems. If not here, maybe in Calc 2. I guess I know some of you are taking Calc 2 starting in the second half of the summer, I guess from July 5th. I mean, we're completing Calc 1 this week. From next week, Calc 2 will begin. I know some of you will be there. So you will be using this property in some of the problems. Okay. And the next one is if you find the area from A to B, it's actually the same if you find the area from B to A with a negative sign. If your function is integrable, of course, we know the function, or I mean, integration will give us the area. But if you do it in a reversed order, let's say not from A to B, from B to A, this will give you the same area, but again, with a negative assigned to it. Can you imagine why? You can actually check the previous problem. If you do it from 3 to 1 instead of 1 to 3, you'll get a negative here. Because now, let me show you. Let me use the same problem. X squared from 0 to 4 it was. Let's say 4 to 0, okay? 4 to 0. So it was 1 over 3x cubed. We need to evaluate it from 4 to 0. Now you can clearly see that our first evaluation will be at 0. So it's 0 cubed minus, we need to evaluate it at 4. And clearly it will be negative 64 over 3, right? Because 0 cubed is 0 and negative 4 cubed is 64. So negative 64 times 1 over 3 is negative 64 third, which is just the negative of what we had here. Can you see that? So if you just, what does it mean? It's really significant. What does it mean? It means if you just change the order, you'll get the same thing, no worries with that, but an alternate value of that. That means if you had, you would have a negative value for this as well, then this would be the positive. That means whatever you have for this, if you change the order, you'll just get the alternate sign, nothing else. The same value, just the alternate sign. If you had a negative value for this, you'll get a positive value for this, and vice versa. This negative sign signifies you can change the order, but you will get an alternate sign assigned to it. You'll get an alternate sign. The value will be same, just the alternate sign. Any question from this? Okay, I think I have enough time to show just one more property, or should I? Yeah, I think I should give you this one last one, and then we'll wrap it up. That is, if you have an interval like this, f of x dx, and let's say that's your a and b. If you can find a point in between it, it doesn't need to be the halfway through. It can be anywhere. Let's say here you have c. All you can do is write like this. Do from a to c. Oh, sorry. And go from c to b. And add this. That's it. This will give you the same result. That means you can have several points in that interval. Then you can find the integral at those points and then add all those. It could be anywhere, as I said. It could be anywhere. Let's say that's my a and b. It could be here as well. Let's say d. So that means you need to find from a to d and from d to b. Then add those. This will give you the same result as a to b. Okay, we'll start from here the next time. So I'll be posting the homework, the last homework for you from 5.1. So keep an eye on that and practice some of the problems. I'll see you tomorrow, okay?